Okay, so last time we left off, we finished our decoding algorithm to decode run length encoded data. I want to take time in this video to actually set up this file in such a way that we can actually turn it into an NES ROM and see it in action and see it actually decoding some level data. In the following video, we're going to add in those exceptions to put in a directive to tell the decoder to then just read out uncompressed strings. But for now, let's set up this file and actually see if we can't compile this and run it. So what do we need? We need the header to run in an emulator. So we put the iNES header at the very top. And I'm not going to go into much detail about the NES header or how it's configured. You can read that on the wiki, the NESDev wiki, and there's a lot of good information on it. For now, I'm just going to cheat and cut and paste. The next thing we need are our vectors at the bottom of the file. And what vectors are is it's where you put some labels that tell the CPU where certain things live in your code. So when the CPU first boots up, it's going to first read the reset vector, and it's going to jump to that to know where the start of your code lives, because it doesn't know where the start of your code is, so you have to tell it by jumping to the reset vector. There's some other vectors here for the interrupts, so let's quickly account for those and put those in our ROM. So this is where interrupts are going to live. So the NMI will live here. We're not going to do anything with it now, so we return from subroutine. The IRQ will live here, and again, return from subroutine because we're not using it. The only other vector we have not taken into account is the reset vector. So we want the reset at the very top. It's going to be at the origin of our code, which we haven't specified yet. We also have to do that. So specify the origin as 8000, and this is the start of our code. The reason it's 8000 is because the CPU addresses all the parts of its hardware at certain addresses. So the cartridge lives at address 8000. So we have to tell the assembler that everything is going to be referencing the address space of 8000. Otherwise, all these labels that we're creating that get converted into addresses when it's compiled aren't going to be in the 8000 range at all, and nothing's really going to work. So we have to set the origin as 8000. Now we can paste in some reset code. Again, I'm going to cheat. I'm just going to take code from my compression routine and take the reset routine right out of that. I don't want to go into too much detail about how that's all set up. That's maybe a topic for another video. I'll quickly run through like the sections of it. This first part that's labeled warm up is waiting for the PPU to warm up. It needs a couple V-blanks before you start using it, and it just won't work properly. Next, we're disabling interrupts, disabling decimal mode, which the NES doesn't use. We're disabling the screen, so no sprites, no backgrounds are being drawn, and we're setting the stack pointer. Next, we're clearing RAM. This isn't strictly necessary, but I find it's a good idea too, just to make sure all the RAM is initialized to 0. And then just to top it off, we're waiting some more V-blanks just for good measure. Now we're in the setup section of our code. So the screen isn't turned on at all. Nothing has turned it on. So this is where you can load palettes, load level data, and that's where our decompression is actually going to be running, is in the setup before the screen is turned on. Let's see, let's kind of organize our code a little bit better. So I usually just put in these comments and these big lines and just label what these blocks of code are. So this is where included files live. This is where subroutines will live. We only have one subroutine, that increment function that takes into account overflows. So subroutines. And so setup, subroutines, included files, interrupts, vectors. The only other last thing I want to add in terms of this organization stuff is at the very bottom, underneath the vectors, you have to attach your your graphics file. So there's 8 kilobytes allotted for graphics tiles that you have to append to the very bottom of your ROM to run properly in an emulator. So this gets included as a binary, and I'm just going to name this graphics .char. Okay. The only other thing I want to fix right now is our exit routine is all wrong. So return from subroutine will return to the subroutine that called the code that is currently running. So we didn't call load level as a subroutine, so this return from subroutine has nowhere to go. So this actually has to be a loop. So exit loop. This is our forever loop. And that should be good. This should be a valid format to compile into a NES ROM. The only things that aren't accounted for are these made-up files that don't exist. So if we try to compile this, we're going to get 2 errors. Can't open file, because these don't exist. So let's actually make those files. I have just a blank, just bog standard vanilla looking level loaded up just for demonstration purposes so we can try to see this thing in action. So we have alternating tile patterns for bricks, and we have a solid 1 tile floor. So it's 1 tile the entire way down. So let's save the characters. So on the very right, these are all the character tiles, and that's what's stored in our .char file at the very bottom of the main file. So let's call this graphics.char. Let's save the name table, which is actually the data that's going to be stored on screen that we're going to be compressing. So save the name table. So let's call this level.name. And we save our palettes. We're only going to be saving the 16 colors that are for the background palette because we're not using sprites, so we're not going to save the 16 colors normally used for sprites. So save palette, palette.pal. That should be all we need. So we have our 3 files, and so yeah, we got include binary, level.name, include binary, graphics. So we're not going to get those errors. It's still not going to work though, because when we open up this level data, you'll see that this is uncompressed. So we're going to be able to compile this, we have no errors, into an NES file, and it's going to open into an emulator. But we're going to get some weird issues because the only code that we have running is trying to decompress compressed data. So let's actually look at this hex and see what's going on. I bet that the PPU is going to be freaking out right about now, and it is. So it's trying to do a bunch of stuff that it's not able to accomplish because it's reading uncompressed data as compressed data and trying to decode it. So it's not going to work. So let's account for that. Let's tell our code that this file down here isn't compressed data. So what we want to add is another directive. So let's detect compressed. Call this detect compressed. And the purpose of this is to detect if data is compressed. And we need to load the first instance of data. We need to compare that with a directive. I use FF for that. That's why it wasn't used before in any of the other directives. So we load first data, compare with compression directive, and break if it is equal to decode. So we actually want to decode if it is equal, otherwise we want to jump to our exit and do nothing. All right. We can compile this. We have a gray screen, which is actually a good sign because that means the PPU isn't doing any crazy freaking out trying to draw a bunch of stuff to the screen with data that doesn't mean anything. So let's go to the hex editor, scroll all the way down, and again, the PPU is now not freaking out. So we fixed that. So now, I think we're to the point where we can try to compress a level and try to decode it. Before we do that, we may need to load our palettes. So in setup, we do have to load palettes. So load palette. The palettes on the NES live at 3F00 in video RAM. To access video RAM, we have to tell the PPU that we want to access it and write through the port 2007. So just like we wrote 2000 to 2006 down here in our decompression code, we have to write 3F00 in that location. So we load 3F store 2006 load 00 store 2006. So this is telling the PPU we want to write to 3F00. The reason is 3F00 is where the palettes live. Okay, now we need a loop. So again, like we did before, we need to use a counter. So I'm going to use X as a counter and just store it up here as a double duty. So we loaded X as 0, use 0 for the PPU write, but now X is already initialized for us. Now we can write a loop for the palette. So palette loop, we load data from palette, which I don't think we actually attached. So we have to attach palette. And then include that as a binary. And it's just called palette.pal. So we reference palette and we index into it, and we store that into the 2007 port. So we're loading colors, and we're storing them to address 3F00 through port 2000. Sorry, 2007. And now we have to decrement X, which is our counter. We want to compare it to the number 16, which in hexadecimal is 10. So we write 16 times. And then break if it is not equal back up to the palette loop. Otherwise, we break out and the palettes are finished. So that should write our palettes correctly. Now we need to compress our level data. So let's take our level. I'm going to rename it to level underscore data because my compression routine is looking for a file named that. Let's go to my compressor, put in this data, compress it. And what this ROM does is it just takes in a file, compresses it, and stores it in RAM. So this first section is the normal run length encoded version of that compressed data. I have another pass. It compresses a second time and takes into account those uncompressed string of singles, which we're not there yet, but we will be soon. So let's take this data. I'm going to copy that. I'm going to paste it in a text file and cut it off again so I can then paste it into a hex file. All right, let's save that as level.rle because it's run length encoded. Let's go back to where our template is working on, so we put this over here. Let's reference that file correctly now. So level.rle. And now this should be the moment of truth. I can't think of anything I missed. I think this should work. Let's see. It does not. Let's figure out why. So I don't see any palette colors. I don't see any characters, but that just could be because they're not colored at all. Let's go to the hex editor, see if anything's freaking out. Something is freaking out. Why? Now I thought we accounted for that, so that may be where our error is. Maybe we didn't account for it correctly. So we detect, we load an FF, which let's check that that is in our file. Open Mac. Okay, so FF is our first piece of data, which then the following piece of data should be our string. Oh, we didn't increment our index. So jump to subroutine, increment our y-index, or else it loaded this, it detected it was FF, it jumped to decode, and then it went to load the same FF and store that as a length. And that's not what we wanted to have happen. So we needed to increment our index again. So this should have fixed it. And it did not, which I'm curious to know why. So hex editor, is our PPU freaking out? It's not. So one step in the right direction. One color got loaded into our palettes. Let's go back. Let's go back to where we're loading palettes. So 3F, load to 2006, 0, load 2006, palette. Oh, I'm decrementing a counter when I should be incrementing a counter. So we initialized our x to 0, and we need to count upwards until we reach 16, not downwards, because then it's going to be trying to decompress or load a bunch of stuff through the palettes. Okay, so that is where we fell short. So increment x counter. Again, moment of truth, I think this has fixed it. It has not. Let's look at our PPU viewer. Okay, we're loading palettes correctly. It's a good sign. Now our screen is not being decoded correctly. Now, is it freaking out? It's not. Well, that's not what I should be seeing though. You know what we forgot? I feel like an idiot. We didn't turn on our screen. So in exit, we have to turn on the screen. So let's actually rename our forever loop because we're going to do some more stuff. So rename it forever. And let's turn on our screen. So what do we have to do? We have to load in some flags to set certain things to happen on the PPU. We store that at 2000. We then load a couple more flags. And this is going to turn on backgrounds and sprites. So this is turning on the screen. This up here is turning on the NMI interrupt, which we're not using. And then we have to actually reset the scroll, because anything you do to the PPU usually upsets the scroll. So let's just reset the scroll. Now to set the scroll, it's register 2005. And there's an X scroll and a Y scroll. So you want to do that 2 times. Now, third time's the charm, I think this should show us our level. And it does. So we have this working correctly. Now the only other thing left is to see you in the next video and try to add in those exceptions for strings of single tiles. So we actually got this working, which I'm pretty happy about. So awesome.